Hello and welcome. In this video, we'll be diving deep into the world of function transformations. This is a fundamental topic in mathematics, especially for IB/AHL students, as it allows us to understand how changing a function's equation affects its graph. By the end of this session, you will be able to identify and apply various transformations, including translations, reflections, and stretches, to sketch the graphs of new functions. You'll also learn how to work with reciprocal and modulus functions, and even how to describe transformations for rational functions. Let's get started with the basics. First up, let's talk about translations. A translation is a slide, either horizontally or vertically, that doesn't change the shape or orientation of the graph. We can represent a translation using a vector, like this one, which tells us to move the graph A units horizontally and B units vertically. Let's see how this works with a function y equals f of x. A vertical translation is straightforward. The graph of y equals f of x plus b is the graph of y equals f of x shifted vertically by b units. If b is positive, it moves up. If b is negative, it moves down. Notice that the b is added outside the function. A horizontal translation is a bit counterintuitive. The graph of y equals f of x minus a is the graph of y equals f of x shifted horizontally by a units. If a is positive, it moves right. If a is negative, it moves left. The key here is that the a is subtracted inside the function and the direction is opposite to the sign. Let's combine these. A translation by the vector a, b transforms y equals f of x into y equals f of x minus a, plus b. Remember, the horizontal shift is inside the function and has the opposite sign, while the vertical shift is outside and has the same sign. Let's work through an example. Consider the function f of x equals x squared. We want to sketch the graph of g of x equals f of x minus 1 plus 3. This means we're translating the graph of f of x by the vector 1, 3. First, let's draw the original function, y equals x squared. It's a parabola with its vertex at the origin, 0, 0. Now, let's apply the translation. The vector, 1, 3, tells us to move every point on the graph 1 unit to the right and 3 units up. Let's take a few key points. The vertex at 0, 0 moves to 0 plus 1, 0 plus 3, which is 1, 3. The point, 1, 1, moves to 1 plus 1, 1 plus 3, which is 2, 4. And the point, minus 1, 1, moves to minus 1 plus 1, 1 plus 3, which is 0, 4. By plotting these new points and connecting them, we get the graph of g of x. It's the same parabola, just shifted. The new vertex is at 1, 3. So to recap, a translation by a, b changes y equals f of x to y equals f of x minus a plus b. The horizontal shift is opposite the sign, and the vertical shift is the same. Next, let's explore reflections. A reflection flips the graph across an axis. First, a reflection in the x-axis. The graph of y equals negative f of x is the graph of y equals f of x reflected across the x-axis. Every y-coordinate is multiplied by negative 1, so points above the x-axis move below, and vice versa. Second, a reflection in the y-axis. The graph of y equals f of negative x is the graph of y equals f of x reflected across the y-axis. Every x-coordinate is multiplied by negative 1, so points on the right of the y-axis move to the left, and vice versa. Finally, a reflection in the line y equals x. This transformation gives us the inverse function, y equals f inverse of x. It swaps the x and y coordinates of every point on the graph. Let's see reflections in action. We'll use the function f of x equals x squared minus 1. First, let's sketch the original function. It's a parabola opening upwards, with its vertex at 0, minus 1, and x-intercepts at minus 1, 0, and 1, 0. Now let's graph y equals negative f of x. This is a reflection in the x-axis. We take every point x, y on the original graph and map it to x, negative y. The vertex at 0, minus 1 becomes 0, 1. The x-intercepts at minus 1, 0, and 1, 0 remain unchanged, as their y-coordinates are already 0. The resulting graph is a parabola opening downwards, with its vertex at 0, 1. Next, Let's graph y equals f of negative x. This is a reflection in the y-axis. We map every point x, y to negative x, y. In this specific case, the graph of y equals f of negative x is identical to the graph of y equals f of x. This is because the function f of x equals x squared minus 1 is an even function, meaning it's already symmetric about the y-axis. This is a great example of how transformations can sometimes result in the original function. Our third type of transformation is a stretch. A stretch changes the shape of the graph by scaling it. A vertical stretch is given by y equals k times f of x. This multiplies every y-coordinate by a scale factor k. If k is greater than 1, the graph gets taller. If k is between 0 and 1, it gets shorter. If k is negative, it also includes a reflection in the x-axis. A horizontal stretch is given by y equals f of k times x. This divides every x-coordinate by a scale factor k. If k is greater than 1, the graph gets narrower. If k is between 0 and 1, it gets wider. If k is negative, it also includes a reflection in the y-axis. Notice the pattern. Vertical transformations are applied outside the function and have the expected effect. Horizontal transformations are applied inside the function and have the opposite effect. Let's apply stretches to our function f of x equals x squared minus 1. First, let's graph y equals 2 times f of x. This is a vertical stretch with a scale factor of 2. We multiply every y-coordinate by 2. The vertex at 0, minus 1 becomes 0, minus 2. The x-intercepts at minus 1, 0 and 1, 0 remain unchanged as their y-coordinates are 0. The parabola becomes narrower or taller. Now, let's graph y equals f of 2x. This is a horizontal stretch with a scale factor of 1/2. We divide every x-coordinate by 2. The vertex at 0, minus 1 remains at 0, minus 1 because its x-coordinate is 0. The x-intercepts at minus 1, 0 and 1, 0 become minus 1/2, 0 and 1/2, 0. The parabola becomes narrower or compressed. Often, we need to apply multiple transformations. The order in which we apply them is crucial. A good rule of thumb is to follow the order of operations or PEMDAS in reverse. First, apply any horizontal translations. Second, apply any horizontal stretches or reflections. Third, apply any vertical stretches or reflections. And finally, apply any vertical translations. Let's look at an example. Suppose we want to transform y equals x squared into y equals 3 times the quantity x minus 1 squared plus 2. Here, f of x is x squared. The new function is 3 times f of x minus 1 plus 2. Let's break it down. First, we have a horizontal translation of 1 unit to the right from the x minus 1 inside the function. Second, we have a vertical stretch with a scale factor of 3 from the ensign 3 outside. Third, we have a vertical translation of 2 units up from the amum plus 2 outside. Applying these in order will give us the correct final graph. If we change the order, we'll get a different result. Now let's move on to a special type of function, the reciprocal of a function. For any function f of x, its reciprocal is 1 over f of x. The graph of y equals 1 over f of x has some very interesting properties that are directly related to the graph of y equals f of x. Let's list the key relationships. First, the zeros of f of x become vertical asymptotes of 1 over f of x. This is because when f of x is 0, 1 over f of x is undefined. Second, the vertical asymptotes of f of x become zeros of 1 over f of x. This is because as f of x approaches infinity, 1 over f of x approaches 0. Third, local maxima of f of x become local minima of 1 over f of x and vice versa. This is because when a positive number is at its largest, its reciprocal is at its smallest. Fourth, the invariant points are where f of x equals 1 or f of x equals negative 1. These points don't move because their reciprocals are themselves. Finally, the sign of the function is preserved. If f of x is positive, 1 over f of x is positive. If f of x is negative, 1 over f of x is negative. Let's apply these rules to sketch the graph of a reciprocal function. Consider the function f of x equals x squared minus 1. We want to sketch the graph of y equals 1 over f of x, which is 1 over x squared minus 1. First, let's draw the original function, y equals x squared minus 1. It's a parabola with x-intercepts at x equals negative 1 and x equals 1. Now let's use our rules to find the key features of the reciprocal graph. The zeros of f of x are at x equals negative 1 and x equals 1. These become vertical asymptotes for the reciprocal function. The local minimum of f of x is at 0, minus 1. This becomes a local maximum for the reciprocal function at 0, 1 over negative 1, which is 0, minus 1. The invariant points are where f of x equals 1 or negative 1. The point negative root 2, 1 and root 2, 1 are invariant. The point 0, minus 1 is also invariant. Now we can sketch the graph. We draw the vertical asymptotes at x equals negative 1 and x equals 1. We plot the local maximum at 0, minus 1 and the invariant points. Then, we sketch the curves, making sure they approach the asymptotes and have the correct sign. The result is a hyperbola-like shape. Let's now turn our attention to modulus functions. The modulus, or absolute value of a number, is its distance from 0, so it's always non-negative. We'll look at two main types of modulus transformations, y equals the modulus of f of x, and y equals f of the modulus of x. For y equals the modulus of f of x, the rule is simple. Any part of the graph of y equals f of x that is above or on the x-axis stays exactly where it is. Any part that is below the x-axis is reflected upwards across the x-axis. The x-intercepts are the invariant points. For y equals f of the modulus of x, the rule is different. First, you discard the entire part of the graph of y equals f of x that is to the left of the y-axis. Second, you reflect the part that is to the right of the y-axis across the y-axis. The y-intercept is the invariant point. Let's see these modulus transformations in action. We'll use the function f of x equals x squared minus 2x. First, let's sketch the original function. It's a parabola opening upwards, with x-intercepts at x equals 0 and x equals 2, and a vertex at 1, minus 1. Now, let's graph y equals the modulus of f of x. We keep the parts of the parabola that are above the x-axis, which are for x less than 0 and x greater than 2. The part between x equals 0 and x equals 2 is below the x-axis, so we reflect it upwards. The vertex at 1, minus 1 becomes a local maximum at 1, 1. Next, let's graph y equals f of the modulus of x. We discard the part of the original graph to the left of the y-axis. Then, we reflect the part to the right of the y-axis across the y-axis. This creates a new graph that is symmetric about the y-axis, with a local minimum at 1, minus 1, and another at minus 1, minus 1. As you can see, these two modulus transformations produce very different graphs. It's essential to understand the specific rule for each one. Let's now apply our knowledge of transformations to a very important class of functions, rational functions. A simple rational function has the form y equals ax plus b over cx plus d. These functions are characterized by the presence of both a horizontal and a vertical asymptote. Any graph of a simple rational function can be obtained from the basic reciprocal function y equals 1 over x by a combination of translations and stretches. To find the asymptotes and describe the transformations, the first step is always to rewrite the function in the form y equals k over x minus h, plus versus. This form immediately tells us the asymptotes and the transformations. In this form, the vertical asymptote is at x equals h, and the horizontal asymptote is at y equals versus. The graph is a translation of y equals k over x by the vector h, v. The constant k represents a vertical stretch and a reflection if it's negative. Let's work through a full example. Consider the function f of x equals 2x minus 6 over x plus 1. Our goal is to find the asymptotes, intercepts, sketch the graph, and describe the transformations from y equals 1 over x. Step 1. Rewrite the function in the key form. We can use polynomial division or algebraic manipulation. Let's use the latter. We want to create an x plus 1, term in the numerator. We can write 2x minus 6 as 2 times the quantity x plus 1 minus 8. Splitting the fraction, we get 2 minus 8 over x plus 1. Rearranging, we have f of x equals negative 8 over x plus 1 plus 2. Step 2. Find the asymptotes. From our new form, we can see that h equals negative 1 and v equals 2. Therefore, the vertical asymptote is x equals negative 1, and the horizontal asymptote is y equals 2. Step 3. Find the intercepts. For the y-intercept, we set x equals 0. F of 0 equals negative 6. For the x-intercept, we set y equals 0. This means the numerator must be 0, so 2x minus 6 equals 0, which gives x equals 3. Step 4. Sketch the graph. We draw the asymptotes as dashed lines. We plot the intercepts at 0, minus 6, and 3, 0. Since the constant k is negative 8, the branches of the hyperbola will be in the second and fourth quadrants relative to the asymptotes. We sketch the curves approaching the asymptotes and passing through the intercepts. Step 5. Describe the transformations. To get from y equals 1 over x to our function, we first apply a vertical stretch with a scale factor of 8. Then, we reflect it in the y-axis because of the negative sign. Finally, we translate it by the vector minus 1, 2. Let's quickly recap what we've covered. We've seen how to translate, reflect, and stretch functions, and how to combine these transformations. We've also explored the special cases of reciprocal and modulus functions. Remember the key rules. Vertical changes are outside the function and have the expected effect, while horizontal changes are inside the function and have the opposite effect. For rational functions, rewriting them in the form k over x minus h plus v is the key to understanding their behavior. Now, to solidify your understanding, here are 5 practice questions. Pause the video, work through them, and then check your answers. Question 1. Describe the transformations that map y equals x cubed to y equals negative 2 times the quantity x plus 3 cubed minus 1. Question 2. Sketch the graph of y equals the modulus of x squared minus 4. Question 3. Find the asymptotes and intercepts of y equals 3x plus 1 over x minus 2. Question 4. Sketch the graph of y equals 1 over x squared. And question 5. The graph of y equals f of x is shown. Sketch y equals f of negative x. Here are the answers. How did you do? If you got them all right, fantastic. If not, go back and review the relevant sections of the video. The answers are now on the screen. Keep practicing, and you'll master function transformations in no time. Thank you for watching. Let's quickly recap what we've covered. We've seen how to translate, reflect, and stretch functions, and how to combine these transformations. We've also explored the special cases of reciprocal and modulus functions. Remember the key rules. Vertical changes are outside the function and have the expected effect, while horizontal changes are inside the function and have the opposite effect. For rational functions, rewriting them in the form k over x minus h plus v is the key to understanding their behavior. Now, to solidify your understanding, here are 5 practice questions. Pause the video, work through them, and then check your answers. Question 1. Describe the transformations that map y equals x cubed to y equals negative 2 times the quantity x plus 3 cubed minus 1. Question 2. Sketch the graph of y equals the modulus of x squared minus 4. Question 3. Find the asymptotes and intercepts of y equals 3x plus 1 over x minus 2. Question 4. Sketch the graph of y equals 1 over x squared. And question 5. The graph of y equals f of x is shown. Sketch y equals f of negative x. Here are the answers. How did you do? If you got them all right, fantastic. If not, go back and review the relevant sections of the video. The answers are now on the screen. Keep practicing, and you'll master function transformations in no time. Thank you for watching.